Welcome to the Cosmic Pie Podcast, episode 40. I'm your host, Wayne Barkhouse, and with me, as always, is
Robert Moore.
Robert. We are broadcasting live, as we
Right.
say, from the campus of the
University of North Dakota. Beats
And-
the alternative.
We could be from home, right?
Right, could be from home.
If we're having a snowstorm, that might be something we might end up doing,
Hadn't thought about that.
You know, get our software all set up so we
Yeah.
can broadcast from home. Now, this is a very special week because this is the last day of classes and the beginning of the Thanksgiving holiday.
Right? The halls were clear of students. They already decided to leave and just take, I guess, zeros for today.
Well,
Yeah.
I'm not saying anything. In fact, that brings up something very important, and that something very important is any opinion that Robert and I may have is our own personal opinion and not necessarily the opinion of the University of North Dakota
Yep.
or anyone associated with them.
That's it.
Exactly.
So just us.
Just us. And by the way, we do have a live chat that's running. So if you have any questions or comments that you like to make while we do this podcast, feel free to use that feature. So, Robert, there's been a lot of things in the news lately, and we've had lots of guests, which is great, but we have less time to talk about these news items.
These news items, so they've kind of stacked up on us.
They
you know?
did. So we got to reach back in the archive a little bit. And the first thing we're going to talk about is this object that's going to kill us all,
Kill us all.
and now not kill us all.
Right.
It's better than the other way around,
It is.
right? Wasn't going to kill us, now it is.
And even if it was going to come this way, I got to say, it's not like it was going to be doing so anytime in the near future.
Right, so we're talking about a white dwarf star.
White dwarf star.
Now, that's a very special type of star. So do you want to tell everybody what a white dwarf is?
Sure.
We start there.
Sure. A white dwarf is essentially the cinder, the remnant of a low mass star at the end of its life. The outer layers puff away, leaving the core sitting there. So think of something about the size of Earth with half of the mass of the sun to about 1.3, isn't it?
Yeah, you don't want to go over 1.4.
1.4. Okay.
Yeah.
So, it's somewhere in about the half the solar mass to about 1.4, 1.3, 1.4 times the mass of the sun.
Yeah.
So it's held up and supported simply because the electrons in there go degenerate, as we say, which just means they've got their velocity, their temperature gives them a velocity somewhere approaching the speed of light.
Yeah, so essentially the object can't collapse in on itself due to gravity because of electron pressure.
Because of electron pressure.
Right. In fact, those type of stars is very important from our point of view, and why is that?
Because our sun should become one in, another 4 billion years.
Probably 6.
Probably 6?
Yeah,
Okay.
it's got about 5.5 billion years left as a main sequence star, and then another billion years to go through the different phases after that to eventually arrive
point.
as the white dwarf.
Yeah.
But
So
yeah,
it
it's pretty
takes a
close.
while.
In astronomy, that's essentially the same number, 4
Right.
billion or 6 billion, right?
That's it.
What's a few billion between friends?
There you go. Looking forward to watching it.
Right. So if you want to show the slide that
Okay.
kind of illustrates what this is all about and why we mentioned or started off with the white dwarf, is a paper that recently came out, and this was earlier this month. It describes a white dwarf star that about a year ago or so, by looking at the data set from a space telescope called the Gaia mission. So this is a European Space Agency mission to put a telescope essentially in orbit around the Earth, and I believe it's in orbit around the Earth if I'm not mistaken. And what it does is it takes very careful measurements of the position of stars. And it also measures their spectra. And from the careful measurements of the stars, they can actually observe stars that are nearby that shift back and forth over the course of time, let's say the course of a year, relative to more distant background stars. And from that, we can actually estimate the distance to the nearest star, the one that's in the foreground. And that's the parallax.
Parallax. And, bottom line, I like to say either geometry works or it's something special to Earth.
Now, do you recall, let's say, I want to test your knowledge a little bit.
Okay.
Do you recall who and when was the first parallax measured of stars?
I do not actually. I'm not a big student of astrometry, so
Okay, so this would have been in the 1800s,
okay.
and it was by a person whose last name is Bessel.
Bessel. Oh,
Yeah,
see, I know him more as a mathematician.
Bessel
The
functions.
Bessel function.
Yeah, so Bessel was the person that actually observed for the first time the shifting back and forth of a nearby star relative to more distant background stars. He
Yeah.
measured stellar parallax.
Okay, because this is tiny, folks. I mean, this is a sub-arc second, and an arc second, think about how big a degree is. Take a circle, divide it up 360 times. Then an arc minute is divide one of those divisions 60 times, and then an arc second is divide one of those divisions 60 times. So all these parallaxes are sub-arc second, smaller than an arc second. So
And as they relate to distance, the closer an object is to us, the larger will be its parallax angle.
right.
And the nearest star to our sun is
Proxima Centauri.
Proxima Centauri. Do you remember how far away it is?
I remember it's just over 4 light years.
Right. So it's just over like 4.2 light years away.
Our parallax of, I think, what is it, 0.8?
Pretty darn close.
Okay.
Very nice, Robert. Very nice. You want to get technical a little more? Another significant digit, 0.77 arc second.
Woot!
You got it, man. 0.8, round it off.
And I did that, folks, because I knew that a parsec is about 3.3 light years.
Yes.
So it's got to be close to an arc second, but not too close.
Yeah, so it's just under an arc second, which means other than Proxima Centauri, every other star has a smaller angle because they're further away.
Has an even smaller angle, yeah.
And so these angles are very difficult to measure. In fact, measuring from the Earth has always been a problem because you have to look through the atmosphere.
Right. And so the star dances around by often over an arc second. So.
Yeah, the blurring effect of the Earth's atmosphere caused by turbulence and so on and so forth causes the smearing out effect, and it's very difficult to measure shifting positions when you observe the star, let's say, at one point in the year, and then 6 months later when the Earth's on the other side of the sun and observe that same star relative to the background. That gives you the maximum baseline without leaving the Earth.
Right.
And those shifts are still that tiny, right? Less than an arc second.
Right.
In fact, it's kind of, it's not funny, but it's important because the non-measurement of parallax, stellar parallax, prior to the mid-1980s was actually used as evidence back in the time of Copernicus and Galileo
Right.
to support the Earth-centered model of the universe, the geocentric model.
Because, of course, if everything's centered and revolving around the Earth, there would be no parallax.
Exactly. And so if we, as Copernicus had described, was orbiting the sun, then you should see the stars, objects shifting back and forth. And you can't see it.
Which the problem is, everything is so far away, the angle is so tiny, and that's the important thing about Gaia is it's outside of the atmosphere. It's outside of all that jiggling and jostling that the atmosphere does with things.
Right, so it's much better precision-wise to measure stars. And like anything else, when you think about it, the best you can do is get in space, get above the effect of the Earth's atmosphere. That really causes a problem.
Mm-hmm.
For example, you get all gemmed up, ready to go to use a telescope. You've been waiting 6 months. You had to apply, and I mean professional observatories in modern time. You've been waiting to, you applied, you got time, so your proposal has been scientifically analyzed, essentially been peer reviewed. They grant you so many nights on a large telescope. You go there, and it rains the whole time.
Right. Or the humidity stays above a certain level so that dew would collect on the mirror.
Yeah, so maybe it's cloudy and you can't observe anything. So what do you do then? Well, you go home empty-handed,
Right.
and you apply again. And maybe you got to wait another year roughly to go by before you get back on the telescope if you're lucky.
Yep.
So above, if you're making observations from space, clearly you don't have to worry about that, about the clouds being in the way or whether it's raining or so on and so forth. And so, more and more emphasis is going to be put on space-based telescopes.
Yep.
The problem is, of course, that is expensive to put up telescopes and maintain them, have people, operating the system while they're in space. And so it's really a money issue. If we had lots of money, if money was not an issue at all, which, to make a joke here, if you look at the national debt, that seems to be the case. just to joke people.
Yeah.
Then you could put up any kind of telescope you want, and the more telescopes up there, the better it would be, because chances are you get time on
You'd
it.
get time on one.
Yeah, and by the way, we talk about the James Webb Space Telescope.
Right.
And when you apply for time, there's only so many hours in a year. And
Right.
the James Webb, like the Hubble, follow this tradition where you apply for time once a year. And there's panels that observe that read all the proposals and rank them in terms of which ones should get telescope time and which ones wouldn't, and so on.
Right.
And what's the priority. And then basically they divvy out the exposure time that you get over the course of a year from a telescope like that, space-based telescope, and then it's just a matter of then having the telescope make the observation, then send you the data. Now, if you think about all the hours that's available in a given year, observing time, right? It just came out, I think it was yesterday, I got a notice, that the James Webb Space Telescope in this current selection round,
How oversubscribed is it?
9 times oversubscribed.
Oh,
That is the total number of observing proposals that were submitted asking for time on the James Webb Space Telescope was 9 times the amount of time available in 1 year. So it would take 9 years to do those observations and fit them in 12 months of observing time.
Wow.
And what that really means is there are a lot of unhappy campers running around today because they didn't get time on the James Webb Space Telescope.
And chances are James Webb is the only telescope that will do the observations that they need.
Well, if I was looking at a proposal and you could clearly do it with the Hubble Space Telescope, I would say
Do it with the Hubble
do it with
Space.
the Hubble Space Telescope. You do not need the James Webb Space Telescope
Or
to
if
do
you
these
could do it with
observations.
one of the large telescope, ground-based telescopes.
Or do it with a ground base. So you always have to make sure you justify why you want the time.
Right.
And it has to be for that particular instrument, like James Webb or like the Hubble.
Yep.
So if you need to make observations, for example, in the infrared, and they need to be very high resolution observations that only James Webb provides, there's your justification.
But I will note also, this is why from James Webb at least, you're not seeing all these you're seeing some pretty pictures, but they're taken inadvertently because they're doing something else, and that just happens to be in the field of view.
Yeah, so it's a product of the science rather than necessarily a focus of the science per se. Yeah,
Right.
because you're not going to get time if you propose, hey, I'd like to take pretty infrared pictures of 100 galaxies, and here's my list of targets.
Right. Somebody's going to look at that, laugh a little bit, and go, wow, somebody's making a good joke.
But if you're super rich and you buy your own telescope and put it in space, well, then you can do what you want with it, right?
Right.
So that's the thing. It's a government-paid instrument, so
Right.
it has to be done fairly, and it's a scientific instrument, so that's the most natural way of using it is this peer-reviewed process. Now, the Gaia mission itself, which is in space to avoid, as you said, Robert, the effect of the atmosphere, it's making the most precise measurements of parallax angles ever done to this moment in the history of humankind.
I think it goes down sub-micro arc second.
Yes, it's like, if I should have brought the number in, it's like 0.00000009 arc seconds is the best it can do.
Wow.
It is amazing when you think about it. In other words, if we could see every star in the Milky Way, and you can't because interstellar matter blocks the view, and the telescope is looking at an optical wavelengths.
Right.
But if there wasn't any interstellar matter in our galaxy, and we're happy it's there, folks, because that's ultimately where the Earth came from.
Right.
And us.
That's future stars and
So
planets.
we want it there, right? If there wasn't any interstellar matter, you can essentially would see every star in the Milky Way, and you'd be able to measure with the Gaia space telescope the distance to every star in the Milky Way.
I didn't know it was
That's
that
how-
good. Yeah, that would be right.
Yeah.
Yeah. Yeah.
And to this date, it's measured well over 1 billion stars in terms of parallax measurements.
Nice.
And all of that data becomes available. And what do you do with it? Well, every once in a while, they dump the data online, as we say, massive core dump. And people can go in there and they can, go around and look. It's available to the public. You can play around with the data. You can look for interesting objects. And what happened a little over a year ago is a couple researchers found an object that was approaching us. So they were purposely looking for things that were inbound. And the reason they could do that is because part of the measurements that Gaia makes is the measurement of recessional velocity or approaching velocity. In other words, using the
Radial
Doppler
velocity.
effect
Yeah.
to measure radial velocities. Yeah.
Yep.
And what they discovered was a white dwarf star that was traveling towards us at a rate of almost 400 kilometers per second.
Seems fast, but that's really nothing.
Now, when you lay out, okay, what is the distance from us to this white dwarf star at the present time, and given our motion and the motion of the white dwarf and where it's going, the white dwarf star would pass within about half a light year in roughly 29,000 years from now. 29,000 years, Robert. If we're still alive, we're eating well.
Yeah.
Okay? So this is not something we have to worry about, but hopefully humankind does. That is, that we're
Right.
still around as a species.
As a species.
And 29,000 years. We haven't wiped everybody out in some global thermonuclear war that
Right.
seems like it can occur at any moment, the way current events are today.
Yeah.
Now, 29,000 years, that is extremely brief, right? That's a flicker,
Flicker of a
in
moment.
geologic time, if you think of that, or even cosmic time. So 29,000 years gets you thinking. Well, a follow-up study, which is what you see here on the slide on the left, there's a copy of the paper, the title page of it and the abstract, then they went and looked at this object. And what was discovered is this particular white dwarf has a very strong magnetic field, more than usual. So if you look at the average magnetic field strength of white dwarfs, this is highly unusual.
Well, that would bleed off energy from the photons.
What it does, though, is it screws up the spectrum of the
Right.
object. So Gaia is automatically, it's like a black box a lot. We hate to say that, but a lot of the software applications that people run, programming algorithms, are black boxes. They are developed, they are debugged, they seem to work. You test it on a few things, then you let it go on millions and billions of objects.
Right.
And then when you find something weird out of the result, out of the output,
Then you go look.
You go back and look to see what's going on. And what they discovered, these authors that looked at this new paper that you see here, is that when they did follow-up observations with a ground-based telescope, they discovered the spectrum has the signs of a very strong magnetic field. Now, how strong? Well, the average magnetic field on the surface of this white dwarf is about 20 million Gauss. And you compare that, what is the Earth's average magnetic field? It's about, Robert, do you know?
About 0.1 Gauss?
Yeah, about half a Gauss.
Half a Gauss.
About
okay.
half a Gauss. So that tells you that this is about, 40 million times stronger than the magnetic field here on the Earth.
I don't think we've got magnets that'll go that
I don't
strong.
think so. I don't
That'd
think
pull
so
like
either.
that'd be like pull the iron out of your blood.
Now, the strongest magnets that I think we have are the superconducting magnets that we use for the Large Hadron Collider and stuff like that. And I don't know the strength of, I don't remember.
Me either.
But they were very difficult to construct. In fact, you might remember, getting down a little rabbit hole here, is when the LHC, the Large Hadron Collider, was first turned on, it only lasted for a brief period of time, and then the magnets quenched, as we say, and destroyed a lot of equipment, and they had the whole thing shut down, and they had to spend months and months to rebuild
It's not
the
surprising.
LHC, essentially, in the area that had the damage because of this strong magnetic fields and trying to get them to work properly.
Right.
And it's my understanding it works now, right? We haven't had any of that type of problem since. So these are very, very difficult. They are right at the edge of our technology in
Right.
terms of getting these things to work. So imagine the surface of a white dwarf like this. Well, what does a very strong magnetic field do? What does a magnetic field do to spectral lines?
Well, like I was saying earlier, it would bleed off energy out of the photons, which are electromagnetic, so that would redshift it.
What does it do to spectral lines if you have a magnetic field?
Oh, it'll split them.
Yeah, what's that effect called?
Zeeman effect.
Yeah, so the magnetic field will split the spectral
Right.
lines. And a very strong magnetic field will split them further than a weaker magnetic field for
Right.
the same object. And we measure radial velocities, either approach or recessional velocities, from the appearance of the spectral lines and identifying the proper ones so we know how much they've been shifted to longer wavelengths
wow.
when the object's moving away,
Well, there's a
or
problem.
shorter wavelengths when it's approaching. In this case, lines were misidentified by the algorithms because of the strong magnetic field effect on the splitting of the
Right.
spectral lines. That's part of the
And I'll mention
process.
the splitting of the lines comes about because if you remember all that P shell, D shell stuff from high school, each of those D energy levels have their own energy, and what you're doing is you get a slightly different wavelength depending on which one the electron falls out of, and so the magnetic field will actually separate that and split those energy levels.
Yeah, and the light from the star has also been polarized because of those strong
I
magnetic
was going
fields.
to mention
right?
the polarization, so
Yeah.
thank you. Yeah.
So that is directly measurable by the ground-based telescope and the instrumentation, the detector that was used. And the other thing is you wonder, what's the big deal, right? I mean, if this white dwarf comes within a half a light year and 29,000 years from now, can't we just wave at it and say, nice to see you later? What's the problem?
Well, one of the big problems is half a light year would make it penetrate the Oort cloud at 1 light year from the sun, which could send a whole stream of comets into the inner solar system.
So the Oort cloud, which stretches out anywhere from 2,000 to 10,000 astronomical units from the sun, and 1 astronomical unit is the average distance between the Earth and the sun. This Oort cloud stretches out so far that the passage of the white dwarf within half a light year can gravitationally disturb the Oort cloud. Now, what do we find in the Oort cloud, Robert?
Lots of comets. Comets all day long.
And if you disturb the orbital paths of those comets, what could potentially happen?
Well, some of them get flung out of the solar system completely. Others get flung in.
Okay, so the ones flung out, not a big deal.
Not a big deal. Who cares?
But the ones flung in,
That's a problem.
that can be devastating for the Earth.
Essentially, this would be, a pray and spray of comets coming in at us.
That's it. So we have inbound comets, a large number of them, what we usually have is normal comets.
Right.
And all you have really to rely on is hopefully Jupiter can help us by gravitationally altering the path of these comets so they don't collide with the Earth. But just by rolling the die, once in a while, a 6 will come up.
Right.
And so once in a while, just by random chance, we're going to get smacked by a comet. And if it's large enough, it can be a global killer.
Global killer. Yep.
So that's a big deal. Now, in 29,000 years, hopefully we have a technology advanced to the point where we can deflect these comets, so at least we will survive.
And I'll point out that they're especially devastating coming from the Oort cloud because by the time they've fallen in this far as to the inner solar system, they are going very fast. And energy scales as the velocity squared. So you doubled the velocity, you've quadrupled the amount of energy it's packing.
That's right, because you think of like kinetic energy.
Right.
And that kinetic energy, we think of it as 1/2 the mass times the velocity squared, or the speed squared, as you would say.
So,
Yeah, these would pack a wallop. So what you want to do in that case, for anyone who listens to this podcast 29,000 years from now, is that you want to catch these things very early.
So you can tweak their orbit a little bit.
Yeah, so you can send something out there and be able to intercept these things and hopefully move their paths to the point where they won't intercept the Earth.
Because I'll mention blowing them up isn't really an option because the question I have for you then is do you prefer to get shot by a rifle or a shotgun?
Now, as it turns out, for this particular object, as far as we know now with this latest paper, it's a non-issue. But why are we spending so much time discussing this? There can be other objects out there, other comets that are inbound right now from the Oort cloud that we're so faint we just haven't picked them up yet.
Right.
And they could be on a trajectory that ultimately hits the Earth. So what do you do in that case? How are we going to get rid of that risk?
I don't think there is a way to get rid of that risk. It's always going to be a risk, as long as there's an Oort cloud.
We got to come up with some way of deflecting these type of objects.
We've got to come up with a way of deflecting them when we finally see them, yes.
And so we need to spend our time doing this. Now, you might go around like Chicken Little saying the sky is falling.
Right. And
but
that's
eventually,
not what we're saying.
But eventually the sky will fall.
Yeah.
It may be next year, and if it does, it's coincidence that we mentioned it today and it's not our fault. Or it may be 500 years from now or more.
Right.
But we should be prepared. And we do think about these things, and people have proposed various ideas. In fact, there was a NASA mission recently that intercepted.
We talked about it.
That's right. That intercepted an asteroid to get some information about what it would be like to change the trajectory of such an object.
And what I like to point out is that it did a better job than what they were expecting.
But that's the kind of things we need to do. We do
Yep.
those observations, do those experiments, so then we have a better idea
Of what will work.
of what impact we can have
Yep.
on these type of objects. No pun intended. You see, in terms of moving their orbits so they don't hit the Earth. Now, this particular object, Robert,
Yep.
it was discovered once you consider that it has a very strong magnetic field on its surface. You can reanalyze the spectrum of the object. And when the reanalysis was done, we discovered that the object has a recessional velocity of 83 kilometers per second.
Ooh,
So it's
going
moving away.
Excellent.
Not coming towards us. Now, there is an uncertainty on all of this, and the
Right.
uncertainty is pretty large. It's 104, plus or minus, as we would say, 140 kilometers per second. So the object could be approaching us or maybe going away. But the thing is, if it is approaching us, it's a very low speed, which means that the Earth, the solar system, is not going to be in the same position when it has its closest approach. So we
Right.
don't have to worry about any disturbance to the Oort cloud, at least for this object.
Yeah.
Okay, at least for this object. It doesn't preclude, of course, we discover something else that's coming near us that could cause the same type
Right.
of influence and damage to
The,
us.
the universe is gunning for us, folks. We've got to get better prepared than what we are.
The other thing it really means is, in science, at some respect, we always look for very interesting objects, something that stands out that's different from the norm, from the average.
Right.
And by doing follow-up studies of these objects, you never know what you find.
Right. I agree.
Yeah.
And it's always interesting. And this is why the data is open and available, is so people can go back and look it over again and say, oh, wait, what's that?
Exactly. Now, the other thing, Robert, that's been in the news, and
Mm-hmm.
it seems to be in the news a lot on a weekly basis, is the James Webb Space Telescope.
Right.
And so we do have some new information. It's really, if you like, a follow-up to some of the stories we've talked about here on this podcast. And this is the idea that we have these galaxies that exist at a very early time in the history of the universe.
Mm-hmm.
So this particular paper then that was published also this month looks at the analysis from a spectroscopic point of view of some of these very high
Oh,
redshift
so it is
galaxies.
spectra.
It is spectra,
Wow.
so it's confirmed. It's not just using the brightness and how bright they appear in various filters and deducing from that what is the redshift or how far away these galaxies are. It's actually measuring their spectra.
spectra.
And from
Wow.
the spectral analysis, the two objects that you see here have redshifts that are, number one, the one that's sort of on the right panel and above there, it's sort of a zoomed up of one area of the image.
Z12?
Yeah, a redshift of 12, and the other one is a redshift of approximately 13.
Holy cow.
You're talking about objects that existed about 330 million years after the Big Bang. So there are high redshift objects, galaxies, that did exist, shortly thereof.
Galaxies form a lot quicker than we've
Well,
been thinking.
to be fair, these are low mass galaxies, as far
Okay.
as we can tell. They are not these massive
Massive.
systems.
Yeah.
But that doesn't rule that those weren't being confirmed
Right.
either. And a lot of them have been and are continually looking into that to see. But there are definitely galaxies that exist very early on, a few 100 million years after the Big Bang. Does that affect cosmology? No.
No.
Does that affect galaxy formation? Yes,
Yes. Greatly.
greatly.
Greatly, folks.
So it speeds up the time in which galaxies would take to form initially.
I'll again point out my own specialization, my own field of planetary formation. We used to think planets took 1 billion years or so to form around a new star. And it turns out that when we started getting where we could see the debris disks around stars, that planets have to form within about 100 million years, or the debris and the dust is gone. The star blows it away. So it's kind of the same thing. We found out that planets have to form very quickly, much quicker than we thought they did. The same thing is going on here. Galaxies form quick. They had to have formed quicker than what we've been thinking.
Now, do you remember the one paper we looked at in a previous podcast that addressed this? by assuming that the universe is on the order of like 28 billion
I remember
years
that
old.
one,
It was
yeah.
that the primary author, somebody from Ottawa, associated with the University of Ottawa.
Right.
And that made the rounds, on different podcasts and streams I noticed on the internet. Everybody was talking about it and so on and so forth. And so you can actually use the data that you see here to test those type of ideas.
Oh, right.
And here's what I mean by that. These objects, these two, let's just look at these two galaxies here that's shown. When you look at the spectrum of these objects, not only can you get information about their redshift, and then using cosmology, you can determine how far back in time you're looking at these objects to note that they're this 330 million years after the Big Bang.
Right.
The other thing that you can look at is their metal content, their metallicity. Now, recall, and we talked about this also before, but this side of the Big Bang, at the very beginning, in terms of ordinary matter, the only thing that was around was essentially hydrogen and helium.
Anything heavier is metal.
Anything heavier than hydrogen and helium, we call that a metal. So oxygen and nitrogen would be a metal, even though it's not the metal you think of, right? On the periodic table, the normal chemistry type of analysis, right? So astronomers like to do that just to keep things very simple.
Simple bookkeeping, because everything past helium is a contaminant anyway.
It's a byproduct of star formation.
Star formation, yep.
So as stars are formed, the first generation of stars would be made essentially of hydrogen and helium. And then as they go through their lives, let's say they're massive stars, they blow up a supernova, and that supernova then expel out material that is cooked inside the explosion of that star, and the end state of that high mass star, and that was what fills up essentially the rest of the periodic table.
Right.
Now, there are other things, of course. We can have colliding neutron stars that build up, the interesting things like gold and platinum and all these wonderful things.
Iridium and tungsten.
Yeah, so mainly it's, let's just go with the exploding stars. Stellar evolution builds up these heavy elements. And so that material gets ejected out into space, and new stars can form from that, if you like, the second generation of stars. So when you look at a newly formed second generation of stars, it would have hydrogen and helium, but it would also have these metals.
Right.
Because the material, if you like, that was formed from is recycled material. And it has these contaminants, as you said, of these metals that were produced in the first generation of stars. Well, then you can imagine these higher mass stars blowing up out of the second generation, creating the third generation of stars, and so forth. And so as you go to another generation of stars, you build up the metal content. What we say in astronomy is the metallicity.
So as you go further back and look at galaxies that are farther and farther away, I would expect there to be lower and lower, progressively lower metallicity.
Bingo! Exactly right. And when you look at the metallicity of these very young galaxies, you find they're metal poor. Now, if the universe was like 28 billion years
That's
old,
plenty of time for a lot of stars to form and blow up.
and these objects are about 13.5 billion years old,
Right.
okay, that means that if the universe formed at 28 billion years ago, by the time these galaxies formed, there was lots of metals
should have been
around,
lots
as
of
you
metal.
suggested.
Yeah.
So these objects should be metal rich, not metal poor.
Right.
But we're getting to the point where we're looking at galaxies that form from essentially primordial, pristine material. They haven't had time, their stars, to build up all of these metals, which is why they're metal poor. That's consistent with an age of the universe that is of the order of 13.8 billion and not 28 billion years old.
Right.
So that goes, once again, another observational piece of evidence that is not consistent with that old age view of the universe.
Right. Again, it expresses more an issue of there's a problem with our view of how galaxies form, not with our cosmology. There's no crisis in cosmology over this.
Yeah, so, and galaxies form, the major force at play here is gravity.
Right.
And it's not a crisis with gravity.
Right.
Because gravity, that modern understanding of gravity is the general theory of relativity. And we've literally done hundreds of thousands of experiments since 1915 to demonstrate there's nothing that's been inconsistent with the general theory of relativity.
Right. I was going to point out that since Edwin Hubble and the expansion of the universe was determined, and the size of the universe essentially, experiments have been done to see if capital G, the coefficient of gravity, tells us the strength of it. In other words, there have been studies to show whether or not the strength of gravity has remained the same throughout the history of the universe. And to date, they're saying gravity has remained the same. It's not changing as the universe gets older.
Yeah, and there's really, we talked about this, a little fancy stuff that you can use, a thing called astroseismology.
Oh, right.
Which can actually, you can probe
Starquakes.
the gravity waves and the pressure waves inside of stars, actually put constraints on it. And this is a paper that was done back in the early 90s. Lawrence Krauss is an author on one of that, paper I'm thinking of.
We know him.
Yeah. And so this was related, if I'm not mistaken, to white dwarfs. So you can put a very tight constraint on the time evolution of capital G, the constant proportionality and the force law of Newton. And that time constraint is such that G hasn't varied hardly at all. A very smidgen amount is possible, but that's it. And I mean a very smidgen amount. Very tiny thing.
It's already a tiny number, so an even tinier number.
Even tinier, which means there's no evidence at all of any time evolution.
Right.
But there is uncertainty in any type of measurement or calculation that you come up with, of course. So so this is telling us that galaxies formed a lot quicker than what we thought. So maybe we're not including in our modeling of galaxy formation all of the relevant physics.
Right.
And it's complicated. There's not just, we say there's gravity does its thing, but of course there's motion of gas. There's all this hydrodynamic type of things that are occurring.
You've got to cool it somehow.
And there's also dark matter.
Right.
Now, we always say or think about when we talk about dark matter, so this is this whatever it is, some type of form of matter that we can detect its gravitational influence on things we can see, and yet we can't see directly the dark matter. We know it exists, we just don't know in what form. But nobody said there wasn't different types of dark matter. And how do you know there wasn't a type of dark matter that existed very early in the universe? Now follow this logic, Robert.
Okay, I'm thinking, okay.
That existed in a very early universe that eventually self-annihilated, so it's no longer around today. And this early form of dark matter collected into clumps. And that caused these clumps to have a higher than average density than we otherwise would think possible. And that normal matter, baryons, as we say, protons and neutrons, would be collected towards this concentration of this exotic form of dark matter, causing things to come together on shorter time scales than we normally would think.
Now, wouldn't that leave some kind of echo? Because the energy of that material isn't going nowhere.
So maybe we should be looking for observational signature of these exotic form of dark matter.
Because immediately I thought of it decays into normal matter. But that screams that we definitely see some kind of effect there.
So there's a form of dark matter that annihilates, that gives rise to an energy field that otherwise wouldn't be there, that actually caused the Hubble tension.
Okay, I like
You remember
that.
the Hubble tension. There's this discrepancy between the expansion rate of the universe over universal scales, like measuring from the cosmic microwave background,
versus over the galactic scale.
Versus more local measurements of the expansion rate of the universe. There's this Hubble tension. And one way around the Hubble tension, people invoke models of this form of dark energy, that existed back at very early time. Well, what happens if the energy field is from the annihilation of this new form of dark matter that actually acted like seeds in the formation of galaxies early on? You see, you can go down that rabbit hole all you want, right?
Right.
And what you're looking for is exactly what you said, and that is, where is the evidence?
Where's the energy? Where's the evidence? Yeah.
So if you can come up with some way of having that and making it work, then maybe you can go off and look in whatever wavelengths region we need to look.
And to the younger folks listening, all I can say is go win your Nobel Prize, because this is one that would get you a Nobel Prize, folks.
Yeah, without a doubt.
Without a doubt.
Yeah. Very interesting stuff, Robert.
Oh, yeah. Oh, yes.
But we have other stuff that's been going on, and this in particular is regarding a new type of space telescope that has been launched a few months ago.
Right.
And this is the Euclid mission.
Right.
Now, the Euclid Space Telescope is a telescope that was designed essentially by the European Space Agencies, the European Space-Based Telescope. And its primary goal in the beginning was to get a very accurate measurement of the stuff we just talked about, and that's this dark energy.
Okay.
So in case you haven't been on our podcast before or don't know anything about dark energy, back in 1998, it was observed, that is discovered by two independent teams of astronomers, that the universe itself is undergoing exponential expansion. Now, prior to that time, we knew the universe was expanding. In fact, as Robert mentioned already about Edwin Hubble, this was something that was determined in the late 1920s.
Right.
And if you think of all what the universe contains, all the mass, all the energy that it contains, we would expect that over time, the expansion rate of the universe should be slowing down. And so in the 1990s, people had thought, well, it's just a matter of trying to measure how much is the expansion rate of the universe slowing down by. That actually gives you a constraint or an estimate of the total amount of matter and energy that's in the universe.
Yep.
And when they went and looked with very precise measurements of what we could do in the late 1990s, they discovered that the expansion rate of the universe is not slowing down, it's speeding up.
Speeding up. Somebody's got a foot on the accelerator.
And the term, it's an accelerating universe. And the term that we use to describe what causes it is dark energy. So Michael Turner coined this term. And really what it says is we don't know what it is.
Right.
We don't know if the vacuum of space is really not a vacuum. There are energy fields everywhere. And one energy field is responsible for the accelerated expansion of the universe, this dark energy
Is it the
component.
quantum foam?
Yeah, I mean, we just don't know, right? People are looking, and it's been well over 20 years, right? In fact, it's been about 25 years now since these observations were done of the discovery of the dark energy, and we still don't know what it is. We don't understand. Now, there are lots of ideas with our fancy, top of the line physics theories, like, for example, quantum field theory and all of this stuff. In fact, you can use quantum field theory to actually make a calculation what would be the vacuum energy.
Mm-hmm.
And that vacuum energy, typically come in two different forms. Number one, it's zero. And prior to 1998, people said, it must be zero. It's consistent with that. We don't see any evidence of dark energy or what became known as dark energy. But the other value that was derived from quantum field theory was the actual strength that we measured in 1998 multiplied by 10 raised to the power, get this, of 120.
So the universe just said, plop.
Exactly. So 1 followed by 120 zeros. That strength.
Yeah, it should have accelerated its expansion to the point.
Immediately after Big Bang, the universe would have blew up at such an enormous size, there's no way anything could form. No galaxies, no stars, no planets, no us. Clearly, that is not the galaxy we live in.
Well,
so you just assume. So you just assume it's zero, right? But in 1998, we did measure this vacuum-like energy, as it turns out, but it has a very low strength. And yet it's there. It's not zero. It's non-zero. It's small, right? Certainly a lot smaller than 10 to the 120 power times that. But what is it?
Well, it's clearly not what we thought it was when we went looking, and we're still looking there.
Well, and the way to help to try to understand this, Robert, would be to observe things you can see.
Right.
To measure the influence of dark energy in the whole history of the universe up to this point. And this is what this telescope was initially designed to do.
Okay, cool.
So it was make detailed observations of various things, including galaxy clusters and so on, to look at the effect of dark energy over time.
Mm-hmm.
It turns out structure evolves differently if there's a dark energy universe versus a non-dark energy universe.
Okay.
You have this accelerated expansion that has an effect on how structure forms. If the universe doesn't undergo this, gravity can clump things together more so than in an accelerated expansion.
So I would expect to see a lot more galaxies and a lot closer together.
In fact, you can put a tighter constraint on the strength of dark energy. And does it evolve over the last, let's say, 8 to 10 billion years? Whatever objects you look at, some of these objects are very far away. So you can look at the time evolution of dark energy. The very simple form of dark energy is one with this energy field, which we coined the cosmological constant, that doesn't change since the beginning of the universe. A constant density field, energy density. Now, Einstein, serendipitously, came up with this idea, right? Back, I think it was in
Yeah, but he called it his greatest mistake.
Yeah, well, that's it, right? So he came up with this idea, but then got rid of it. And the
Right.
reason why he came up with this idea is that shortly after the general theory of relativity came out and people applied it, including Einstein, to the universe, it was discovered that the universe should be unstable. It should be either expanding or contracting. But at the time, astronomers would tell Einstein, well, Einstein, the universe is stable. It's neither contracting nor expanding. This is before Hubble in the late 1920s.
Yep.
So Einstein in roughly 1917 came up with a paper showing, well, if I put this fudge factor in my field equations, the equations that would describe the universe from his general theory of relativity, I can get the universe to be stable. Turns out he was wrong when people really analyze in detail, but hey, let's give Einstein a break, right? So he introduced what was called the cosmological constant. Then, of course, in the late 20s, it was discovered the universe is in a state of expansion, is not stable, not static, as we would say. So Einstein, of course, is said to have said, oh, and Homer Simpson nowadays would have went, don't. And he didn't need to introduce that fudge factor. He removed it from his equations. But, of course, once you let the genie out of the box, it's always there.
Right.
Well, it turns out we need that genie today. And that genie is this cosmological constant. In fact, all the observations that have been done up to this point in time in 2023 are all consistent with this constant energy density, this cosmological constant, described exactly the way Einstein introduced it back in 1917 or so.
So again, what we're seeing is that it doesn't change the further back we look with galaxies further away.
But there's an uncertainty on that, of course.
Of course.
And the Euclid mission is designed to better understand that constraint, to make it more precise, to reduce the uncertainties in these type of measurements.
Sounds good.
So we'll see what comes out of this, right? So we have to wait a few years before we can do the observations and then crunch the numbers, right?
Because somebody's got to reduce that data, crunch the numbers, and then interpret them and say, okay, well, this means this.
Exactly. But in the meantime, one of the things you want to do once you have your space telescope up there, regardless of the purpose, is to show people it works.
It works.
And here's an image taken with the telescope of the Perseus galaxy cluster. Now, this galaxy cluster is about 10 billion light years away. So it's not in our backyard, Robert. Not even close.
Not even close.
But the other way of thinking about it is every galaxy that you see in this galaxy cluster, you're seeing the light left it 10 billion years ago. You're seeing the galaxies as they were 10 billion years ago.
Yep.
You're not seeing them as they are today.
Right.
It just took that long for light to reach us over that vast distance to this
Well, that's
object.
what happens when the space you're trying to traverse, the space itself is expanding, so you're getting further away. Yeah.
It's amazing when you think about it. But let's look at something closer to home.
I'm looking at it and going, man, every one of those dots is actually a galaxy, isn't it?
Yes, exactly. You can't see, the only individual stars you would see is something in the Milky Way that's in the way.
And by the way, how I would tell that is there would be what we call diffraction spikes around a star. So, yeah, wow, okay. Let's look at the next image.
Yeah, so this is a galaxy much closer to us. This is a galaxy, it's a dwarf irregular galaxy, as we would say. The full version, if you like, is on the left. I zoomed in on the top right corner, and that's what you see in the right panel. But let's just look at the one on the left. So this is a dwarf galaxy. If you like the catalog numbers, NGC 6822. It's about 1.6 million light years away, which is a lot closer than 10 billion light years.
A lot closer, yeah.
So we're seeing the galaxy as it was about 1.6 million years ago.
About the time the dinosaurs started roaming the Earth.
1.6 million years
ago.
ago.
1.6 million.
Yeah.
Derp. About the time hominids started
yes,
roaming
by
the
the
Earth.
time humans were starting, the early humans were starting to roam around on the Earth. You had me worried there, Robert, for a
I
second.
needed 2 more zeros. My brain just didn't work. Sorry.
Now, if you zoom in on that top right panel, which is the panel on the right there, you see this beautiful purple-like structure. Those are star formation regions in this dwarf galaxy. The amount of resolution is amazing in terms of the structure you can see. And I zoomed in a lot to be able to see those objects, and it still doesn't wash out the detail.
And you can see what I'm talking about. All the stars have spikes.
The diffraction spike for the diffraction spikes for the brighter stars, exactly right. Now, another object that this telescope looked at, and they released the data, is the next one. If you want to bring up the next slide, Robert, please.
Pretty.
This is a globular star cluster. This is much closer. In fact, it is in orbit around the center of our own home galaxy, the Milky Way.
Yep.
Also name of a good chocolate bar, by the way. This globular cluster is about 7,800 light years away. So we're seeing it as it was 7,800 years ago.
About the time the Egyptians started getting their stuff together.
Okay, now you're making a connection with the pyramids and this globular cluster.
Well, it
aren't
was
you?
old, but that would be older than the pyramids.
Okay, so Stonehenge. You're making
Yeah.
a connection with Stonehenge. There's a podcast there that we could put. We'll just
Yeah.
call it a different name.
Yep.
Made up stuff or
Made up
something like that.
Oh, Lordy.
But so these globular clusters, by the way, are extremely old. These are about as old as the galaxy itself, essentially. They can be upwards from 10 billion to 13 billion years old. In fact, they are so old, they are kind of the first large structures that formed this side of the Big Bang.
Right.
It's amazing.
They're generally metal poor, like we mentioned. So they're closer to the primordial stuff that came out of the Big Bang.
Now, the history of globular clusters is long, but one of the interesting things was prior to the discovery of dark energy in 1998, the globular clusters were determined to have an age that was older than the universe itself. It would be like you're older than your mother. How
Right.
could that possibly be? Obviously, the ages are not correct.
One or the other is not correct.
And what it was is that we didn't know the universe had the dark energy component. And when you plug in the value of the dark energy and then you change the cosmology, that also changes the age of the universe. So now the universe is about 13.8 billion years old, as far as we can tell, where the age of the oldest globular cluster is on the order of about 13 billion years, which
Yep.
means you are now younger than your mother.
Right.
Everything is safe. Woo!
Woo.
But just looking at it, the star cluster itself, one of the things when we look at globular clusters that it's hard to resolve the central region of these clusters because the density of the stars is
Too many
so
stars.
great, too many stars. But clearly you can see well down into the central region of this cluster because of the high resolution of this telescope because it's in space.
To any aspiring authors out there, you could do a story about a planet in a globular cluster because they would never know night. There's just too many stars close around.
Exactly. It'd be like perpetual suns in the sky
Right.
all the time. Be interesting when you think of that.
Really interesting.
And what
Yeah.
type of astronomy would people develop who live there?
Right.
Now, the other thing we are looking at this week is a new result that came from the James Webb Space Telescope. And this is by looking at something you can see in the nighttime sky at this time of the year. It's starting
And
to
with
rise.
your eye, you can see.
And with your eyes. If you're in a dark location.
Yeah.
If you're in the middle of Times Square in New York City, you're not going to be able to see this object.
You're not going to see it all.
You have to get if you're in New York, you have to get way
Way out of-
outside into the rural area, get away from the suburbs and the urban area.
Get up into the Gainies. Go upstate.
And what you can see then is a stellar nursery. And this is the Orion Nebula. It's in the constellation of
Orion.
Orion. And the Orion Nebula is on the order of about 1,600 light years away. It's not in our backyard either. It's quite far away. But it is the, if you like, prototypical example of a location where stars are actively forming today.
Right.
We have nurseries and hospitals where we find babies.
This
Where
is
you
a stellar
find baby
nursery.
stars? Things like the Orion Nebula.
Absolutely. Wonderful. I love taking pictures of it myself.
And
Can't
it's-
get anywhere near this detail.
Exactly. And the thing to note here is with the James Webb Space Telescope, you're looking in the infrared.
Right. Which
And-
means you get past a lot of the dust.
Right, which means you can see more details of what type of stuff happening.
The new stars being formed, the new stars, and the disks around them because they'll be glowing a little higher in infrared. And I want to zoom in on this.
Exactly. In fact, what are those four stars? And there's more in this image. What do we call it? Do you remember?
The trapezium.
Yeah, and if you actually look at that, those stars saturate. There's diffraction spikes everywhere.
Right.
You really can't see. You can see some fainter stars in the trapezium area, but
Right.
in this image, they're just so bright that literally they saturate the detector, which is amazing when you think about it. And these are, in an amateur telescope, these things are relatively faint. They're not that bright, the trapezium
Right.
stars.
You say that, but you will saturate your detectors on a ground base with a 12-inch telescope at about a 2-second shot. So these are still bright stars. It's just, you look up at the end of the sword of Orion, you're looking at them.
Yes.
and they look kind of fuzzy. Well, the little reason they look fuzzy,
You're looking
they're
through the
sitting in
cloud
that nebula.
material. Yeah, exactly right. Now, the interesting thing also about this, if you want to understand the whole process of star formation in nitty-gritty detail, which we don't know,
Right.
these are the type of objects, the Orion Nebula and other star formations.
This is where we want to look to learn.
Yeah, exactly. And so we'll see what comes out of studies like this. It'll
Yeah.
be quite interesting.
I love it.
Now,
Great.
the thing that made the news, and we talk not only about astronomy, but also space exploration in general, of course, is what happened Saturday morning. And what happened was the second launch of Starship. So, Robert, you want to turn to that?
Oh, yeah.
Now, this was a long time in coming. The first launch was in April. And in that launch, the first and second stage did not separate.
So they
And
blew it up.
ultimately, it was blown apart. It took a while to blow it apart because there was some kind of delay in the destruct system they had on board.
Right.
But eventually it blew up. And of course, the U.S. government had to look at it carefully to make sure it was safe to launch from the location it was being launched from before SpaceX decided to do another test flight.
Right.
And it is a test flight.
It is a test flight. So let me dispel something right there with saying that. Folks, you want your ships to blow up on test flights, because now you can look and see, okay, what went wrong. What you don't want is for one of them to blow up on a real flight. So if there's any problems, you want them to appear now.
Robert, you had me worried for a second.
I know I kind of stammered there, and it
I
sounded...
thought you said the other S word.
Yeah,
You did
no,
not say that, by the way.
I did not say
It was
that. I
ship.
stuttered.
Yeah. So yeah, it's very important. You got to do these test flights. How are you going to know how to fix it? If we knew, if we knew in nitty-gritty details how to construct these rockets without them going wrong at any moment, that is, we could construct them so they were perfect.
On try one.
On try one, well, we wouldn't have test flights. We just go right in the operational phase.
Right.
And you put a very expensive payload on board, and away they go, type of stuff, right?
And kablooey.
Now, the second test flight, which was launched Saturday morning, as I mentioned, the first stage was important because you might remember, or you could go back and look at some clips that was all on the internet everywhere. And when the first stage was launched back in April, not all of the engines lit up at the moment of liftoff. It has 33 Raptor engines, which consume liquid helium, liquid methane and
methane.
oxygen. Okay. So these are methane as the fuel here. Okay, so it's unusual. A lot of rockets don't do that. I think SpaceX is the people that have been pushing the use of methane, if I'm not mistaken.
Okay.
And so in this launch, this time, notice every single one of those 33 Raptor engines are firing. They're burning properly, as it turns out. So the first stage was a complete success. All engines lit up prior to liftoff. The rocket lifted off the launch pad like it was expected to and carried the stack, the whole rocket, up into the heights, as far as we know, the altitude that it was supposed to be at and at the speed it was supposed to be going.
Yep.
Now, the last time what happened was, as I mentioned already, the first and second stage didn't separate properly, so they reconstructed all of that. And what they are doing now is something they call a hot staging. What it really means is you light up some of the engines of the second stage before you separate from the first stage. So they get up and running, and they aid, if I'm not mistaken, in the separation of the two stages.
Well, they would, because they blow it back.
And they have vents around the interface of the two, so that hot gas can go out the side of the rocket and not cause, an explosion or something of the rocket itself when they start lighting up. And the second stage has 6 engines, 3 larger engines outside and 3 in the center, smaller engines, right? Mm-hmm. And so what happened was they lit up the engines prior to staging. Those engines, as far as I know, they lit up normally. Then the stage separates, and then all 6 engines are fully going at this point of the second stage. The second stage then accelerates away from the first stage.
Right.
And in the video, you can see the first stage starting to tumble. Ultimately, you wanted to turn it around, and it will land back unmanned, somewhere. And that's like they do with all the SpaceX rockets now when they send up Starlink on missions and so on and so forth. And so ultimately, you reuse these stages to lower the cost.
Lower the cost, yeah.
So what happened in this case, as you can see it coming back and tumbling, all of a sudden the first stage blew up and parts are flying everywhere. Now, why it blew up, I'm not quite sure if it's self-destructed.
I don't think they're sure yet.
Or the lighting of the engines in the second stage caused some kind of a potential, maybe a leak eventually, a structural failure that led eventually to a leak, which then caught on fire and then blew everything up. We don't know. And so, but the first stage had done its job. It had accelerated the rocket up to the right speed and altitude so that the second stage takes over. The second stage did its thing, and almost at the end, or at the time in which the 6 rocket engines of the second stage would shut down,
Right.
there was apparently an explosion. It was very hard to tell because it was so far away from the camera, and I think it wasn't crystal clear when it was launched. There was a little bit of cloud there, that you see some kind of almost like a shockwave effect, some venting, some kind of event had happened roughly 20 seconds or so prior to the nominal shutdown time of the second stage. And then all data was lost, as far as I know.
Okay.
And so it might have been an explosion. They don't know if it was triggered by the onboard self-destruct system or it was some other event that happened. They're analyzing the data.
You've got to go and analyze
we'll
the
know
telemetry.
eventually.
Yeah.
But literally, this object was almost put on the proper suborbital flight in this case that we expected to be going. It was so close to being a good mission in sense of getting
A complete mission.
to getting in a hot firing all the way to where you want
Yep.
to go, the right direction and speed and altitude and so on. So test flight number 3 should do it, hopefully, once we understand what happened here. But the important thing is this rocket is designed to take up a heck of a lot of cargo. In fact, Robert, this Starship, when it launched, it generated about twice the thrust of a single Saturn V that we used to launch humans to the moon.
That's a lot of cargo.
This Starship is a moon rocket.
Yes.
It is also a Mars rocket.
Yes.
We are going to explore our solar system using this type of technology.
Mm-hmm.
And that's the
Absolutely.
importance
Yep.
of it. We're going to do it better,
Faster
cheaper,
and faster.
and faster.
Yeah.
And that's what we want. The cheaper it is to carry every pound or kilogram of payload, the more we can advance and to develop the exploration of our solar system.
The more you can lift with each rocket, the cheaper it becomes per pound.
And if you want to be part of that, then
That's
get
it.
your education.
Right.
Come to places like the University of North Dakota. Either come and join us here directly on campus, or if you can't do that, please consider taking classes online. Nowadays, you just need a computer and an internet, and you can learn about everything.
Right.
And that is great. I wish they had that when I was younger. I've been taking classes in high school, online.
Or at least looking in on them, right?
Definitely. So it's
Yeah.
quite interesting the way the technology evolves and makes it easier for people to learn. That's the
You're
way
a
to
little
do
out
it.
of the frame.
Now, the other thing, too, is that we will have another podcast next week on November the 28th at 3 p.m. Standard Time. In fact, we'll have another special guest. Parker Johnson will be visiting us
Right.
here. And to note that at some point, though, Robert, we will be taking a break, just to give a heads up, for
Right.
the holidays.
Yep.
And so we'll let people know ahead of time what's going on with that. And then in January, then we will start season number 2. Yeah, it's amazing.
Yeah.
It's been almost
It's been a
since
year.
then.
Almost. Right at
Now,
it.
we always leave a quote at the end of our podcast, and we'll do the same today. This quote, and it is fitting, is by Robert H. Goddard,
Woohoo! Father of rocketry.
father of rocketry. In fact, he invented the first liquid-fueled rocket.
Yep.
And so the quote from Goddard is this: "It is difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow." Thank you very much for watching.
Thank you, folks. Have a good day.